This video covers the multiple fundamental variables that we will use when we discuss angular kinematics. The sooner you can memorize these variables and their relationships, the easier this upcoming chapter will be. So let's begin. Say that we have a satellite that is orbiting Earth. After some period of time, it will orbit a given distance around the Earth. When it orbits, it is a given distance away, which we call the radius, and it rotates through a given angle, which we call theta. The distance the satellite covers when it is orbiting is called the arc length. You can think of arc length as like a section of a circle. So angular displacement is described as the change in angle when an object undergoes rotational motion. The SI unit for angular displacement is radians. Radians can be a little bit confusing sometimes, so we will briefly review what a radian is. To calculate the number of radians in a given distance, you simply divide the arc length by the radius. Another important thing to remember about radians is that there are 2 pi radians in one full rotation or circle. So if an object undergoes one full rotation, its angular displacement would be 2 pi radians. Angular velocity, which is represented by the Greek lowercase letter omega, is how much angular displacement occurs within a given time interval. The units for angular velocity are radians per second. We also have angular acceleration, which is represented by the Greek lowercase letter alpha, and this is how much change in angular velocity occurs within a given time interval. The units for angular accelerations are radians per second squared. So hopefully you are beginning to see a pattern here with the relationship between angular and linear variables. We are also able to relate angular and linear variables together through the following equations. Displacement of a rotating object is equal to the radius times the angular displacement. Tangential velocity is equal to the product of the radius times the change in angular velocity. And tangential acceleration is equal to the product of the radius and the angular acceleration. So hopefully you are also able to recognize the trend here between our linear variables and our angular variables. Our last equation that we are already pretty familiar with is the equation for centripetal acceleration, which is equal to the linear velocity squared over the radius. Now we can see that it's also equal to the product of the angular velocity squared and the radius. So at this point in the video, I suggest you pause and make sure you really understand these variables and where they're coming from and their relationships with one another. So next we're going to walk through a few problems with our new variables and equations, which I place here in a condensed format. So this is our first question. A wheel in a car has a radius of 0.5 meters. As the car travels down a section of highway, the wheel makes 1,000 complete rotations. How far did the car travel? So first, let's label the variables we were given. We know that we have 1,000 rotations and a radius of 0.5 meters. And we want to find the total linear displacement, also known as delta x. First, we should find out how many radians this tire experiences over the time interval. We know that there are 2 pi radians in one rotation. So in order to find the total angular displacement, we're going to multiply the number of rotations by 2 pi. And we see that the total angular displacement is 2,000 pi. Alright, so now that we know the angular displacement, let's try to calculate the linear displacement. And the linear displacement is equal to the radius times our change in theta, or angular displacement. So we have 0.5 times 2,000 pi, and we get a total linear displacement of 1,000 pi, or 3,141 meters. Let's do another problem. A point 1.5 meters away from the axis of a rotating disk is accelerating tangentially at a rate of 22 meters per second squared. Calculate the angular acceleration. So once again, we know that the radius is 1.5 meters and that the tangential acceleration is 22 meters per second squared, and that we are looking for angular acceleration. We know the relationship between angular and tangential acceleration is this equation here. So we can plug in our known values and solve for the angular acceleration, which is 14.7 radians per second.